So we proceed today. We're discussing fluid mechanics. We're still handling the past paper from July, August 2024. Now, as usual, it also has 8 questions where people are required to choose any 5. But for purposes of revision, that's not our business. We go through each and every question so that you enjoy the revision package. Considering that we've discussed various principles, this also gives us a chance to break the boundaries, look at some of the things perhaps we might have not touched, because in the exams, that is normally very common. So right away, let's pick up question 1. We are not going to ignore the definitions. We are equally going to consider them as per tradition. So explain what is meant by each of the following. There's surface tension, capillarity, compressibility. Yeah. So surface tension. So we're talking about the effect that is caused mainly by the force of cohesion at the free surface. In other words, it's saying you talk about the force of cohesion where the particles of a liquid try to hold together. Then in the end, they will try to hold onto the surface. So as a result, you have what is known as surface tension. When we're doing calculations, we also have what we'll be calling the surface tension force, or simply the surface tension. Capillarity, you have both cohesion. Cohesion is the formation of what looks like bubbles of liquid where they adhere together and make such. Then adhesion, the sticking together. So when you look at the two effects coming together or being combined, then you have capillarity. In other words, this is also called capillary action. It happens by way of the free surface. When you can put a small tube, you see liquid rising above or below the free surface. That effect still refers to what we are calling capillarity. Compressibility is simply the ability of a fluid to undergo change in volume under the action of external pressure. So we normally expect gases to be highly compressible. The liquids are almost incompressible because their compressibility is very negligible. So here is our question. It's talking about the velocity distribution for flow over a plate is given by U is equal to 2y minus y squared, where U is the velocity in meters per second at a distance y meters above the plate. Determine the velocity gradient and shear stress at the boundary and at a distance of 1.5 meters from the boundary. Take the dynamic viscosity of the fluid as 0.9 Newton seconds per square meter. So, as usual, let's try to arrange the information we have. First, we've been given that this is the velocity distribution expression, which is U is equal to 2y minus y squared. Now, from here, tell me about the gradient. The velocity gradient becomes du dy. We'll come to this. We're going to differentiate this expression. Let me pick my usual. Then y is the distance from the free surface, or from the boundary, or rather from the boundary going into the liquid. So at the boundary, as well as at a distance of y is equal to 1.5 meters from the boundary, that is where we need to find those conditions. the gradient as well as the shear stress. That's what we are required to find. So the coefficient of dynamic viscosity is 0.9 Newton seconds per square meter. Hey, that's all. Then let's go for this expression. We said velocity gradient for u is equal to 2y minus y squared is du dy. Now, if I take you back to the rules of differentiation, this is raised to power 1. And when you differentiate, it means you multiply this power by this coefficient here, 1 times 2, and you also subtract 1 here. You do the same for this one when you differentiate dy squared dy. I mean, this one with respect to y, you multiply by this power 2 in front. Then this power again, you subtract 1. Now, 1 minus 1 is 0. Any number raised to power 0 is 1. So you end up with 2 times 1. Even if you multiply 1 times 2 times 1, the result is just a 2. Then here, 2 minus 1 means you have y raised to power 1. Then 2 times y gives us this 2y you are seeing here. Now, I always say that when you're dealing with the application of these principles in the application package, what you do in mathematics is slightly a step further to make sure that when we come to the application, you can't even feel the maths part of it. You enjoy the application because we pick it from the point where you started this topic of differentiation, though we know it goes deeper than this. So here we are. Our velocity gradient for this fluid is simply du dy is equal to 2 minus 2y. Now with this gradient, we need to find first a velocity gradient, the actual, not just the expression, the velocity gradient at y is equal to 0 at the boundary, as well as at the depth of y is equal to 1.5 meters from the boundary. So at the boundary, the condition is that y is 0. So let's go back to this expression. Where there is y, we put 0. So it looks like this. The velocity gradient is 2 minus 2y. So we're saying 2 minus 2 times z, where there is y, we've put 0. So meaning that you end up with du dy. This 2 minus 0 is gone. You simply have 2. Now, if you look at this du dy, you're talking about meters per second times z. You can already see that, or rather divide by what? Divide by a meter for dy. So these meters cancel out. You just remained with this, which is in 1 over second. Now, when you write this expression in this format, second is raised to power 1 already. So if it comes up there, this is the unit. Second is raised to power 1. So that is our velocity gradient at the boundary. Can we repeat this with y at a distance of y is equal to 1.5 meters? Let's get the gradient even at that point. So we go back at y is equal to 1.5 meters. I will again substitute in this expression. So I bring it back. Du dy is equal to 2 minus 2y. So 2 minus 2, in place of y, I put 1.5. So when you do that, you realize that 2 times 1.5 is 3. So from your mathematics, 2 minus 3 is supposed to give us a negative 1. So this one is du dy is equal to negative 1. We don't end here because we need to find two things. The first one is what we found, the velocity gradient. Then let's proceed now to get the shear stress at the boundary, as well as at the distance of y equals 1.5. at a depth of 1.5 meters from the boundary. So here, shear stress, the formula, if you go to Newton's law of viscosity, we say shear stress is equal to coefficient of dynamic viscosity times du dy. Now, what makes it interesting is that du dy, we've just calculated it. So in our case, at the boundary, we got du dy as 2. So if I put it back, I'll have mu du dy is equal to 0.9 multiplied by 2. The 0.9 is this, according to our data. It's representing the coefficient of dynamic viscosity. So what you get when you multiply that by that is the shear stress of 1.8 newtons per square meter. Let's repeat this now. This time around, we just change. We're going to consider at distance y is equals 1.5. We're saying 1.5 meters from the boundary. What is going to be our shear stress? Du dy is -1. With these conditions, let's find our shear stress. So again, we invite the formula for shear stress, which is shear stress is equal to du dy, which is equal to, in place of shear, coefficient of dynamic viscosity, 0 point that. Then du dy, which is the gradient, we found it as -1, meaning that our shear stress is -0.9 newtons per square meter. So this is how you get the two values. This is how you find the two answers. You've already gotten the shear stress as well as the gradient. Question number B. Wait a minute, just a minute. Something I want to quickly check up. Okay, I think this was just a typo error. This one we are here with, I believe it's supposed to be part C. So this is supposed to be our part C. I might have just made a mistake. This is part C. A clean tube of diameter 2.5 millimeters is immersed in a liquid with a coefficient of surface tension as 0.4 newtons per meter. The angle of contact of the liquid with the glass can be measured to be 135 degrees. The density of the liquid is 13,600. And also we have what will be the level of the liquid inside the tube relative to the free surface of the liquid. So here we are trying to calculate for the capillary rise, capillary action. What will happen? So here, let's collect the information we've been given. First, we have the surface tension force, or the surface tension is 0.4 Newton per meter. Then we also have the specific weight of the liquid. The specific weight of the liquid, we're going to take this. It's the density in kg per cubic meter. So 13,600 multiplied by, we're converting this kg to newtons, times 9.81. So when we say 13,600 multiplied by 9.81, we end up with 133,416. This is our specific weight for mercury. So here I am. That's my 133,416. What about the diameter of the capillary tube? The diameter of the capillary tube that we've been given, and it's clean so that the capillary action can easily take place without interference, is 2.5 millimeters. So all we do now is to convert the millimeters to meters. When you're doing this conversion, you divide that number by 1,000. So 2.5 millimeters divided by 1,000, you get 0.0025 meters. Then let's proceed. What about the angle theta? It's 135 degrees. Anything else? I believe we're done for now. This is the information we have. With this information, we have one question to solve. So the capillary rise, which is given by letter S, the height is 4 multiplied by the surface tension, cos theta, over specific weight times the diameter of the capillary tube, or the diameter of the tube we're using. Then let's do the substitution. First thing you can see, 4 remains 4. Surface tension is 0.4. Multiply this by cos theta, which is cos 135. Specific weight is 133,416. 133,416. The diameter of the capillary tube is 0.0025. So enter all that in your calculator. The answer you should be able to find is negative 3.392. Negative 3.392 has one simple interpretation. We're simply saying that the surface of the liquid is like that. You've put your capillary tube. So in this case, instead of this height of the liquid going up above this free surface, the rise in this tube is like that. It is a drop. It has gone down instead of rising. So hence, it is negative, meaning you have such a height from the free surface up to there where we are. So what you have is a negative height, because instead of rising, the capillary action has happened in the opposite. It has gone down. And this is what we expect for capillary action. Sometimes it can go up above the free surface. Sometimes it can go below. That's very normal. All right, so that was question 1. Let's pick up the second question. Definitions as per usual practice. Static pressure. Define pressure head. Barometric head. So what are our responses? Static head, this one we can even call it hydrostatic pressure. This is the pressure which is exerted on a surface, exerted on a body, because of the weight of the fluid exerting on that body. That is our static pressure, or pressure at rest. What about the pressure head? So this one, we're talking, when we say pressure head, we use letter H. So it becomes the height of fluid column corresponding to a specific pressure. For example, 10 kilopascals, but you say it's 2 meters of, then you mention the liquid that you're using, the column of liquid you're using to compare that pressure, and gives you the same equivalent. Then you to review the actual pressure, it requires you to use this formula here, as you see where we are going, like that. Specific weight times height. So pressure head, therefore, so happens that it's the pressure divided by the specific weight, giving you that head, the height. So what kind of liquid are you dealing with? They need to also tell you the height you have. But if you can calculate backwards and review what pressure that was, it will give you what that one was from the beginning. Barometric pressure, you use a barometer to measure this kind of pressure. Now this one, we're saying that it's also known as the atmospheric pressure. When we refer to the atmospheric pressure, we're talking about the pressure exerted on surfaces in the atmosphere. Others say it is the pressure due to the weight of the atmosphere, which usually sounds a bit too hectic, because here we're simply saying when you refer to atmospheric pressure, You're talking about the pressure exerted on surfaces by the atmospheric air. As long as you live in this atmosphere, you have the effect of this pressure, depending on where you live. What is the altitude where you live from sea level and things like that. So that is where we talk about this. So here we have a question, says we have a YouTube manometer used to measure the pressure of oil of specific gravity 0.85 flowing in a pipeline. Its left end is connected to the pipe and the right limb is open to the atmosphere. The center of the pipe is 100 millimeters below the level of mercury of specific gravity 13.6 in the right limb. If the difference in mercury level, just a minute, let me arrange it properly. If the difference in mercury level in the two limbs of the manometer is 160 millimeters, determine the absolute pressure of the oil in the pipe. Let's see. There's some data we can arrange here. Yes. So first, let's draw this as they have raised it. This drawing, you come up with it on your own, following that language there. So it says the center of the pipe, when you draw the pipe like that, and you connect a YouTube manometer because it is connected on the left end, we have a pipe. So this is our left-hand side. Then we've been told that this level of liquid in the manometer, from there to the center of the pipe, the center of the pipe is 100 millimeters below this level here. What does it mean? It means you're considering this height. You're talking about this height from the level of the mercury in the right limb coming down to the center of the pipe. The number is 100 millimeters. Then they further say, the question also further says, the difference in mercury level in the two limbs of manometer is 160. What does this even mean? It means on the left-hand side, your level is here. It's from here to here. So you have this height here. Let's call it, for example, maybe H1, okay? Then this one on the right-hand side, from the same level, going up to the top, this, for argument's sake, for now, maybe we decide to call it as the H2. What do they mean by the difference in mercury level? They mean this H2 minus that small one, H1. The whole H2, this whole distance here, minus that. In practice, we're simply saying this height from here to here, cut away, remove this, we don't want it. So you measure the difference, which is from here going up. It is the one we've been given as 160 millimeters. 160 millimeters. And of course, we are going to make sure each of them is converted because we're not going to work with millimeters here. We are going to make sure everything is actually in the meters. All right, now, with that in mind, let's prepare the information provided. First, we have the specific weight, which is 0.85. So 0.85 multiplied by 9810. This is our procedure for converting from specific gravity or relative density to specific weight. Knowing very well that specific weight is the parameter we're going to use. So we have specific weight 8,338.5 Newton per cubic meter when you multiply these two values. Then the height, because from here to here it's 100, and this is 160. If you subtract this 100 minus 160 minus the 100, it gives you this height here. which is 60 millimeters. So 60 millimeters to convert to meters, you divide by 1000, you end up with 0.06. Then specific weight number one, which is this one now, for the mercury, we say the 13.6 that we were provided with, multiplied by 9,810, then we've converted, it becomes 133,416. H1. H1, we're talking about this height here on the mercury side, on the right-hand side, 160. The task we have is, first of all, to convert it to meters. So 160 divided by 1000, you get 0.16. Then we can now apply Pascal's law for the YouTube, the formula we use, or it basically simplifies to pressure at A, pressure in the pipe is equal to specific weight 1 times height 1. This is for the mercury minus omega H, just those two. Then specific weight 1 is referring to the liquid in the manometer, which is 133,416 times H1, which is 0.16, minus specific weight is 8338.5 times the height, which is 0.06. When you enter them, you get 20,846.25. The question was not asking for gauge pressure. The question was asking for absolute pressure. What we've calculated is the value you get from gauges, so it's a gauge pressure. And we have to convert. The expression is that this absolute pressure is equal to the sum of the atmospheric pressure and the gauge pressure. In this case, our gauge pressure is PA, pressure in the pipe. So we add atmospheric pressure to that. So you have 20,846.25 plus the accepted value for atmospheric pressure, the accepted standard for this one is 100,000, 100,000. So you add 100,000 to this and you get 120,846.25 newtons per square meter. So we've calculated the absolute pressure as the question was requiring. You see that journey. Right, so now we can safely say we're done with question number, the second question. So we proceed to question 3. Now, question number 3, asking us first of all to basically, it says Reynolds number RE is defined as a ratio of the inertial force to the viscous force. Show that the Reynolds number of a given fluid mass, rho, and dynamic viscosity mu, flowing at a velocity u through a pipe of length L is given by Reynolds number is equal to density. I think this is supposed to be u, not with the v I've put here. That L over v. So here we simply take up those two. We are saying, according to the definition, we've been told it's a ratio between the inertial force and the viscous force. So question is, what is the inertial force? The inertial force is density times u squared L. The viscous force is coefficient of viscosity times u times L. So when you bring together those, replace Reynolds number as Fi over F of V, plug them in that expression, and simplify, then you end up with the expression as it was provided. So you have, of course, up here, this is just our u. I don't even know where I'm getting the u from. So that is supposed to be u. The u will cancel out, and then you end up with that. Now, here's our typical example. It says, we have a 6-meter long pipe inclined at 20 degrees to the horizontal. The smaller section of the pipe, which is at a lower level, is 100 millimeters in diameter. And the larger section of the pipe is 300 millimeters, meaning that the larger section is at the higher end of this pipeline. The smaller section is at the lower end. The bigger the section is at the higher end. Then, of course, the pipe is uniformly tapering. And then water in the smaller section is running at 1.8 meters per second. Assuming the datum line passes through the center of the pipe at the lower section, determine the pressure difference between the two sections of the pipe. Now, here's the thing. We are told it's like this. Sorry. Let's put it properly. Here, this pipe is tapering uniformly, assuming from here going to there, and this is the center of our pipe. This is the center of our pipe there. And the datum they're referring to, which is passing through this lower end here, is like that. We are basically talking about this line here. And meaning this angle we have here is the 20. That's our 20 degrees. Now what I'm going to do is this. This is my section 1, and this is my section 2. How do I get the height? Because this is where my datum is passing, meaning that this one doesn't have a height. It gives me the fact that my Z1 is 0 because it's right at a point where this is positioned. But to get my Z2, which is this height here, from here to there, I can even do this. Let me just do that. This height here up to here. We can already see that this is making a right angle triangle. And following the SOHCAHTOA, you can say that this height I'm talking about, which I'm going to call Z2, Z2. So Z2, and this is the length of our pipe. Z2 divided by L. What does it give me? it actually gives me sine theta. Sine theta, because Z2 is actually opposite that angle we're dealing with. So sine 20 in this case. So if I'm looking for Z2, that height, it will be my Z2. My Z2 is going to be equal to L sine 20. So I'll put my L here, then sine 20. L sine 20. So I put the 20 over there. So with this in mind, I already have the length of the pipe as 6 meters. So we'll use these parameters to do just that. Here's our data then. Z1 is 0, like we said, it's right there. Length of the pipe is 2 meters. Z2 is 6 sine 20. L sine 20, L is 6, and that's the one. So 6 sine 20 gives us 2.0252. Then A1 is pi d squared over 4. So A1 is pi times 0.1 squared over 4, giving us 0.007854. Area 2, same formula, pi times 0.3 squared over 4, and we get 0.07069. That is the area for section 2, this side. Section 1 is smaller, so it's here. Velocity 1, this one we've been given that the smaller section, the velocity of the water at that section is 1.8 meters. Let's make progress then. Specific weight. Interestingly, when you read this question, you don't see any clue to tell us what the specific weight is. Maybe they've given us the density, specific gravity, but the lead they've given us is here. They're saying this is water. Water is a standard fluid. This is a standard liquid, and all you do is refer back to the specific weight of pure water. Since we know that density of water is 1,000, when you multiply that 1,000 by 9.81, you get this value here. So our specific weight is 9,810. 9,810, that's what we're going to use. So then we only have one velocity, the other velocity is missing. So we use the expression for continuity of flow, the expression for the discharge, which is A1 V1 is equal to A2 V2. From there, you decide to make V2 the subject because that's the one we're looking for. V2, make it the subject of the formula. So we have A1 V1 over A2. Divide both sides by A2. So we substitute. A1 is 0.007854. Velocity in the smaller section, we're given as 1.8. Area 2 is 0.07069. Velocity 2 is 0.2. When you look at this, you can already see that our information is now complete. And all we can do is just do the substitution. So what do I do? The question, oh yeah, first of all, the question was asking us to find the difference in pressure between the two sections. So we want to find what is P1 minus P2. So if I want, I can plug the numbers and start working. But here I decided to make it a bit interesting. I want to make P1 minus P2 the subject of the formula. You can already see that here, these sharing a common denominator, which is omega. So I might as well write it this way. Just as this side, I can do the same. I think I'll do it in the next step. P1 minus P2 over omega is equal to, this Z1 has crossed the equal sign, so it's carrying a negative. Same thing with V1 squared over 2G. It has also done the same, so here we are. Because Bernoulli's equation in full is Z1 plus P1 over omega plus V1 squared over 2G is equal to Z2 plus P2 over omega plus V2 squared over 2G. So when you reach a place like this, you are ready. All you can do is multiply both ends by this so that you just remain with P1 minus P2. Here we are now combining V2 squared over 2G minus V1 squared over 2G. They have the same denominator, so V2 squared minus V1 squared. Then the omega is outside. Now I can substitute. In place of omega, I have 9810. In place of Z2, I have 2.052. Z1, height number 1, height in the smaller section, height at the lower end. We said this is 0. Velocity 2, we just calculated it here. It's 0.2. Velocity 1 was already given in the question. It was 1.8 meters per second. So 1.8 squared over 2 times 9.81. So here, when you enter this in your calculator, take your time. Sometimes you enter this, get one value, then add to that. And in the end, P1 minus P2 supposed to give you 18,902.52. So the question was simply asking for this, meaning we leave it there now. Let's go to question 4. Question number 4 says, distinguish between gauge pressure and absolute pressure. Gauge pressure, we're saying this is the pressure measured above or below the atmospheric pressure, or the pressure measured with the help of gauges or pressure measuring instruments. Whereas sorry, this is defining atmospheric pressure. Make a correction. Gauge pressure, we're saying this is the pressure measured with the help of pressure measuring instruments or gauges, or the pressure that is measured with the atmospheric pressure as the datum. That is gauge pressure. Then atmospheric absolute pressure is the sum of the atmospheric pressure and the gauge pressure. Seems like we didn't even finish we ignored the definitions, but of course, these are things that are correct in the final document. Pascal's law of pressure, here we simply say that for a liquid at rest, pressure is evenly distributed in all directions. Then comes our question here. Using this diagram, it says a single column manometer is connected to a pipe containing a liquid of specific weight 0.8, as shown in figure Q4 below. The ratio of the cross-section area of the reservoir to the cross-sectional area of the right limb is 100. Taking the specific gravity of manometric fluid as 13.6, determine the pressure in the pipe. This is the pressure in the pipe we're looking at, and that's a pipe. What information do we have? First, the liquid in the pipe has specific weight as has specific gravity as 0.8. So we convert it to specific weight, it becomes 0.8 times 9810, we get 7848, 7,848 newtons per cubic meter. Then we also have now the liquid in the manometer, which is, in this case, it's mercury. Same thing, multiply it by 9810, we get 133,416. Which height are we dealing with? We have two heights. There is this height of the liquid, which we are going to call H, is 300 millimeters. Then we convert it to meters by dividing by 1,000. we have 0.3 meters. The next height, this is height number 2. From there going up, this is 500 millimeters. So if you divide that by 1,000, you get 0.5. The ratio between this cross-section area and this is 1 over 100. That's what we've been given. In fact, they're talking about what is on the right limb, this and this reservoir. So as you can see, we've managed to pluck out every piece of the data. Now we can proceed with the working. So when we decide to apply Pascal's law, there is one small thing we need to do, which is taking care of this disparity between the size of the reservoir and what is coming up here. Apart from our normal consideration of application of rather Pascal's law, we also have this differential, which is coming as a result of the difference in cross-section areas between the reservoir and this right limb column. Who is to be blamed? It's this height here on the right limb because this liquid is coming out and going there. So what are we going to do? We are going to say the difference between the two liquids multiplied by the height on the right limb, then we multiply it by the ratio. We just plant that factor to that. Added to it is now specific weight of the mercury times the height of the mercury minus, this is just the normal expression we use for a YouTube manometer, minus omega H. This is omega for the liquid in the pipe and also H for the liquid on the left-hand end, referring to the same liquid in the pipe. Let's do the substitution. That area ratio is 1 over 100. This H1 on the right end is 0.5. Omega 1 is 133,416 minus what we are calling omega, which is the specific weight for the liquid in the pipe, is 7,848 plus. Then we have omega 1 H1. This is 133,416 times the height of the liquid on the right is 0.5 minus 7,848 times 0.3. When you do that, these are the numbers you have. The first set, which is this one here, gives us 627.84. The second set, referring to this, gives us 66,708. The last one, which is this last part here, gives us 2,354.4. Then you can now just get your answer, and we have 64,981.44 pascals or newtons per square meter. If you are working in kilopascals, you should be able to get it as 64.981 kilopascals. So that is how we go around this question. Question number 5 says, a thin plate in the form of an isosceles triangle of base 4.5 meters and altitude 5 meters is immersed horizontally in an oil of specific gravity 0.83. The entire plate is completely submerged such that its depth from the free surface of oil is 340 centimeter. Determine the total pressure on the plate and the center of this pressure. Okay. Total pressure and center of pressure. Let's pick the information. First, we have B, the base of this isosceles triangle. Isosceles. So when we're talking about an isosceles triangle, we're referring to a triangle like this, where these two sides have the same height. So the base we've been provided with is 4.5. 5. This is our base. Then the height, this height here, we've been told it is 5. This is here, 5. 5 meters. Everything is in meters. So then, that's it. Now, first things first, let's get the area as a result of this. Area of a triangle is half base times height. So we have half times the base, which is 4.5, times the height, which is 5. Then we get 11.25 square meters. Specific weight, the specific gravity that we have here is 0.83. So now that you have 0.83, we just take ourselves through the same procedure. 0.83 times 9,810, and we get 8,143.3 newtons per cubic meter. Bar X, now, here's where things get a bit interesting. This is my free surface. Then this one, which is triangular in nature, has been positioned horizontally, meaning that the distance from here coming to where this is, where it's the center, where it is the center of gravity, the center of what? The bar X is that same depth we've been given, which is 340 centimeters. So 340 centimeters, divide that by 100, you get 3.4. 340 divided by 100, the answer you get is actually 3.4. So this one was positioned not vertically, but horizontally. From your knowledge of engineering drawing, when you put something horizontal and you're looking at it from across, this is all you will see. But if you look at it from the top, you'll see something like that. You'll see the actual shape. So meaning that for the horizontal one, the advantage that we have is that the center of pressure as well as the center of gravity for the plate, the distance they occupy is the same, the depth they have is the same. So that's why the question is simply going straight for the total pressure on the plate. That's it. And we'll talk about that center of pressure as we go. So we go to B. Oh, sorry, the working. This is our total pressure acting on the plate. It's omega A by X. So omega is 8142.3 times area is 11.25 times the bar X, which is 3.4. So what you get, sorry, it's not in pascals. No, this is actually a force. So it's in newtons. Now, it's also asking for the center of pressure. Like I said, when you are dealing with a body which is immersed horizontally, this one we have as bar X is equal to, in fact, what I'm saying is what we are calling the depth of the center of pressure, which is bar H, is equal to bar X, which is the same 3.4 meter, 3.4 meters. That's it. So here, just like that, this is our answer for the set depth of the center of pressure. That's all. Then we also have another one, similar, says a triangular window is immersed in seawater as shown in the diagram. Calculate the resultant force on the window and locate the center of pressure. Find the location of the center of pressure. So as we practice, let's pick up the information provided. First, it's like today we're dealing with these triangles. So for the area of a triangle, we have half base times height. So half BH, half multiplied by the base is 40 centimeters. 40 divided by 100, you have 0.4. The height is this one here. 60 centimeters. So 60 divided by 100, you also get 0.6. When you multiply 0.4 by 0.6, you get 0.24. Half of 0.24 is 0.12. What am I even saying? Enter these values in your calculator, you'll get this answer here. 0.12 square meters, that is our area. Bar X, this is now asking for us to find the depth of the center of gravity from the free surface. Now here, when you're dealing with a triangle, you have to be very cautious because what we've been given by the shape of a triangle is that where the center of gravity is, it's actually here. We say h over 3. This height over 3. But this is from the base. So if I have to come from the nose there, from the tip coming down, then it will be 2/3 h, 2 over 3, multiplied by the height. If you add 2/3 and 1/3, you should get a full number. So what are we even saying? We're saying that that depth of the center of pressure, center of gravity rather, coming to bar X, is going to be, you add this number to this one we have here. This number is 25 centimeters. 25 centimeters divided by 100, you have 0.25. Plus 2/3 the height is this from here up to this point where the center of gravity is for this shape. So 2/3 times 0.6. Put them together in your calculator, you get 0.65 meters. Next, let's find the moment of inertia about the center of gravity for a rectangle. So we call it IG. The formula is BH cubed over 36. BH cubed over 36. Our B is 0.4 multiplied by our H is 0.6 cubed. Everything divided by 36. So with this, what do you get? You get 0.0024. And this is in this. There. It is in those units there. Next, we have specific weight. Now, this specific weight is already here, but the weight has been presented. This is seawater. It is in kilonewtons per cubic meter. All we do is let's convert it to the normal unit where I'll say 10.08 times 1,000. Then 10.08 times 1,000, we have 10,080 newtons per cubic meter. So this is the information we have for this shape at hand. And what do we do now? What do we proceed to do? We can now do we go to the working. So here we're saying that the resultant force acting on the window, this is P. P, the formula we use is omega AX. So we have specific weight times area times bar X. Specific weight is 10,080. Cross-section area we've corrected. I mean, the area that we found was 0.12. Bar X, we calculated this as 0.65. So meaning our total force acting on the window is 786.24 newtons. 786.24 newtons. So that's the force we have there. What about the distance from the free surface to the center of pressure, the depth of the center of pressure? So bar H is equal to IG over A bar X plus the same bar X. Now let's get this straight. If this was at an angle like that. We include sine squared theta on top there, and the rest remain the same. But anyway, that's a story for another day. I know there's a paper where we're going to do that very smartly. So here, the depth of the center of pressure is equal to Ig over A times bar X plus the same X bar. Let's do the substitution. Our Ig was 0.0024. Then our area was 0.12. Bar X was 0.65. So we're adding this the same 0.65. When you compute this, you get 0.681. Now let's listen to this. The depth of the center of pressure, the depth of the center of pressure, as you can see, is higher, it's lower, because it's normally below, whichever, whether it's immersed with negative gradient or name it, that's how they behave. So meaning if you find that your bar H is smaller than the bar X, then there's somewhere there's a problem there which needs to be sorted out. You're dealing with a very special angle somewhere. But otherwise, it's just a clue, just a quick guide to that. Question number 6. Now here we're talking about flow. The question was asking differentiate between pipe flow and open channel flow. So in pipe flow, we're talking about liquid that is flowing in a confined pipe within the boundaries of a pipe, interacting with those. In open channel flow, we're dealing with a section of a column where liquid that is flowing is equally open to the atmosphere, and the confines are just within the dimensions of that channel, the open channel. So the other one is enclosed. This other one is open, and even of course, some pipes can be big, but some channels can also be abnormally big. Hence, even affecting the way flow may behave. Then it was also asking us to list just 2 losses associated with pipe flow. Now here, the loss of head, the major one is friction. Then we have these others that flow in like sudden enlargement, sudden contraction, bend in a pipe. Then we have things like fixtures, exit to the pipe, entry to the pipe, all of them. So pick any 2, you're good to go. Now this is, sorry, seems like I have an issue with this letter. This is part C. Water is flowing in a pipe of diameter 350 millimeters and 75 meters long at a velocity of 2.8 meters per second. Find the head lost due to friction using which formula? Number 1, Darcy-Weisbach's formula. Number 2, Chase's formula. Given that Chase's constant is 55, assume kinematic viscosity to be of water to be 0.012 stock. Okay, now here we proceed with the working. First thing we have is the diameter of the pipe, which is 350 millimeters. So we divide by 1,000, we get 0.35. The next thing we have is the length of the pipe, which is 75 meters. So 75 meters, it's all fine. We leave it like that. Then we also have the velocity at which this water is running. The water is running at 2.8 meters per second. Chase is constant, which is C. C is equal to 55. Then we have the viscosity, the kinematic viscosity, which has been given as 0.012 stock. Now, this 0.012 stock it means something similar to what we were dealing with under dynamic viscosity, which was given in poise. It's not the SI unit we have to work with, no. So what do we need to do? You get this number, divide by 10,000. Then if you say that, divide by 10,000, you have 1.2 multiplied by 10 raised to the power negative 6. Just a conversion to make sure you're dealing with the SI unit that will fit in and use everything as it is. So let's pick up the first one. We find loss of head due to friction when we use the first formula, Darcy. So with Darcy, we first of all need to fix Reynolds number. Reynolds number is Vd. This is the velocity times the diameter divided by the kinematic viscosity. So this is equal to V is 2.8. Diameter of the pipe, 0.35. Kinematic viscosity, what we're using is 1.2 multiplied by 10 power negative 6. And the answer we get is 816,666.67. Now, for this one, all this trouble we're going through, we need to use this formula. And looking at the kind of number we are having, it's between 4,000 and 1 million and 10 power 6. So meaning we use the formula, which is F, more like our coefficient of friction, is 0.0791 over Reynolds number raised to power 0.25 or raised to power 1 over 4. So 0.0791 divided by 816,666.67 raised to power 1 over 4. It gives us this beautiful number here, which is 2.628 by 10 power negative 3. That is our friction coefficient we're looking for. A special character there. So then let's find then the loss of head due to friction using Darcy's formula. So this one is given by 2FL V squared over DG. This is the value we've just found, the coefficient. L, the length of the pipe. V, the velocity of liquid. The velocity at which the liquid in the pipe is moving. D is the diameter of the pipe. G is very familiar. This is one of our favorites. That is acceleration due to gravity. So let's now proceed. 2 is 2, then F, we pick this number. 2.628 times 10 power negative 3 multiplied by, again, 75, which is the length of the pipe. The velocity at which this fluid is moving, we already given as 2.8, so 2.8 squared. Divide by 0.35 times, 0.35 is the diameter of the pipe, then we multiply by G. Our G is 9.81. Whatever you do after that, however you handle your calculator nicely, just make sure you don't mix up numbers. You take your time, get one value for the top, one value for what is below there, and then this is what you get. Loss of head due to friction using Darcy formula, Darcy-Weisbach formula, is actually 0.9 meters. Let's repeat the process. This time around, we use Chase's formula. With Chase's formula, we're going to improvise, rather, we're going to include this hydraulic mean depth or hydraulic radius, represented by letter M. Depending on which book you're using, some other books use letter R because it's hydraulic radius. So this is A over P. Cross-section area is by D squared over 4. P is the perimeter. The formula for perimeter is pi d. What does this even mean? You can cancel this. So cancel that. You cancel the d and also part of the d so that you remain with d power 1. So meaning the whole expression now dissolves to this d over 4. So we're looking for this, just use d over 4. You're good to go. Our d is 0.35 divided by 4. 0.35 is the diameter of the pipe divided by the 4. You get 0.0875. According to Chase's formula, the velocity of the pipe flowing there is supposed to be equal to c, the square root of mi. This letter I is simply the ratio between the head loss due to friction and the length of the pipe. So what we have now is V equals CMI. We can just substitute. The velocity is 2.8, C 55, M is this one we found here, 0.0875. Multiply by that I. So you square both sides of the equal sign, make I the subject of the formula, then you're going to get your I as 0.02962. Now, we already said this I is the ratio between the head loss due to friction and the length of the pipe. So what are we going to do then? Let's make this I the subject. Sorry, we want to make this head loss the subject because that's what we want. So you multiply both sides by L, and hence you have this. HF is equal to L times I. So let's substitute our L, the length of the pipe is 75 meters. I is this number we just found here. So 0.02962, and hence our HF is equal to 2.22 meters. 2.22 meters. That is our head loss due to friction. You can already see that when you use Chase's formula, this number is higher compared to Darcy-Weisbach. Question number 7. In relation to pumps, we are told to define the following terms or explain them. Manometric head. We're saying this is the head against which a pump has to work. So theoretically, that head is the one we call the manometric head. So it's supposed to represent the increase in head along there, which should be achieved by your pump. Volumetric efficiency is simply or here, of course, in the document are correct. It could be that I might have been a bit busier. In volumetric efficiency, we're talking about the ratio between the actual flow rate and the one you calculate, the theoretical one. Suppose when we talk of the theoretical efficiency, I mean the theoretical flow rate, we don't take care of the losses because it's theoretical. There will be other things. Suppose there are no losses, that ratio gives us that. And remember, this is efficiency, so you may decide to express it as a percentage. Hydraulic losses, these are various. So we're saying that these are losses due to, majority of it is friction, turbulence, the dimensions in the pipe, blockages in pipe, name it, pipe bends and all that. Those are hydraulic losses. Basically, they end up piling up into hydraulic head losses or pressure head losses. So here's our question this time around for an impeller. The impeller of a centrifugal pump having an external diameter of 500 millimeters and an internal diameter of 250 millimeters with an outlet width of 50 millimeters is running at a rotational speed of 1,200 RPM, working against a head of 48 meters. The velocity of flow through the impeller is constant and equal to 3 meters per second. The vanes are set back at an angle of 40 degrees at the outlet. Determine A, the vane angle at the inlet. Hey, this is supposed to be part one. It's okay. This is part two because we're repeating the letters. And the parent letter is B. So this one is supposed to pick up Roman numerals. But anyway, this is just those. So we avoid these. So vane angle at the inlet, work done by the impeller on the water per second, then the manometric efficiency. Those three are the ones we are looking. So here's our information. First, we have the diameter, the external diameter of this impeller. It's 0.5 meters. The internal diameter is 0.25 because in there we were given 250 meters. The width at exit is 0.05 because it was 50 millimeters. So we've converted. As we practice, we simply divide that 50 by 1,000 and we get this number. At what speed is the shaft connected to the impeller running? 1,200 revolutions per minute. What is the manometric head? It's 48 meters. Now, we've been told that the velocity of flow through the impeller remains constant. What we are trying to say is that velocity of flow 1 is equal to the velocity of flow 2. VF1 equals VF2, and they're having the same number, which is 3 meters per second. The exit vane angle is 40 degrees. And we use letter phi to represent that. So with this information, let's start by finding the inlet vane angle. So the first thing we deal with is the absolute velocity. The absolute velocity, which is U at the inlet. U1 is pi d1 n over 60. Even U2, when we're looking for the absolute velocity at exit, it's supposed to be pi d2 n over 60. So pi dn over 60 is the general formula when you are getting your answer from revolutions per minute to meters per second. So what are we going to do? Let's substitute. This is our pi. The internal diameter, which is d1, is 0.25 multiplied by rotational speed is 1,200. Everything is supposed to be divided by the 60, and the answer we are having there is actually 15.708. Tan theta is equal to VF1 over U1. Velocity of flow at inlet over absolute velocity at inlet gives us the angle for the inlet vane. So the inlet vane angle. So meaning that we can therefore say theta is equal to tan inverse of that formula, that ratio, VF1 over U1. So then theta is equal to tan inverse of our VF1, velocity of flow, 3, velocity of flow at inlet, divided by the absolute velocity at inlet, 15.708. The same one we found here. So that's our U1. So with this in your calculator, you should get your inlet vane angle as 10.812 degrees. Work done by the impeller. What do we do? First things first, let's find the absolute velocity at exit. Like the same formula we used for inlet, but we just changed the number. So it's pi d2n over 60, which is equal to pi, diameter 2 is 4.5, n is 1,200, then divide by 60. So you get 31.415 meters per second. Since we're looking for, we want to transpose for this one, we now proceed to substitute in this expression where the absolute, the vane angle at exit tan phi, tan that angle is equal to VF2 over U2, the absolute velocity at exit, minus the velocity of wheel at exit. That's VW2. So tan 40, here the phi is 40, is equal to VF2 is equal to VF1. So it's 3. U2 is this one we have just found. So 31.415 minus the targeted character, which is VW2. So from here, we can make this the subject, cross multiply and make VW2 the subject of the formula. We have VW2 is therefore equal to 27.841. Then we have the discharge. The formula for the discharge is on the exit, especially we're talking about the exit side, pi d2b2 by vf2. Now here, the whole of this is representing the area of flow. So it's like we're saying area 2 times velocity of flow 2. So it is equal to, then we can now just do the substitution. I have pi times d2 is 0.5, then multiplied by again, b2 is 0.05 times velocity of flow number 2, it is in 3. So that is our complete set. And all I do now is just to compute this in your calculator. And what do we get? We get 0.2356. This is our discharge in cubic meters per second. So then the work done by the impeller on the fluid per second then is, we now do the calculation of that. The formula that we're using is specific weight times discharge over acceleration due to gravity. Then we multiply by velocity of wheel 2 times U2. So we can substitute specific weight of the water, 9,810, times the discharge is the one we've just found here, which is in 0.2353. Then divide by 9.81 times velocity of wheel 2 is this one we got here, 27.841. Again multiplied by U2. U2 is this one here, 31.415. So 31.415. All this put together gives us our work being equal to 206.061. Eh? 206.061.65 joules. So we're saying work, therefore, if you put it in kilojoules, it will be 206.06 kilojoules. Manometric efficiency is G times manometric head over VW2U2. Then, of course, you multiply by 100. So then we substitute G, 9.81, times our manometric head is 48, divided by VW2 is 27.841, times U2, which is 31.415. Again, multiply by 100. You get 53.83%. Final question. Distinguish between a pump and a hydraulic turbine. Now here, we look at the function of a pump. A pump will convert mechanical work into mechanical energy into hydraulic energy, whereas the turbine does the opposite. It will use hydraulic energy to convert it to mechanical, or you can call it kinetic. So we have now a reaction turbine working at a speed of 450 RPM under a head of 120 meters. The diameter at the inlet is 1.2 meters and the flow area is 0.4 meter per meter square. The angle is made by the absolute velocity and the relative velocity with the tangential velocity at inlet at 20 and 60 degrees respectively. Determine volumetric flow rate, power developed, hydraulic efficiency. Information provided. Please, you can ignore the diagram. I think it's faint, so can refer to it later, but it's quite faint, so we don't need to stress our eyes. The rotational speed is 450 rpm. The head against which it's working is 120 meters. Diameter at inlet is 1.2 meters. Then comes my favorite. This is our area of flow. We can call it A1, area 1, area at inlet. It's this pi dB, pi dB. Pi d is the perimeter, b the width. So the whole of this is equal to that. So then we have absolute velocity angle. This is the one we've been given, that is our alpha, 20 degrees. Then velocity, relative velocity at inlet, relative velocity angle at inlet, that is the 60 degrees. So this is talking about this one, VR1, and this, and the U, the angle between them, that, the other one there is 20. So let's find the U1 first of all. U1 is pi D1 N over 60. Pi times, our D1 was 1.2, times N, which is 450. Divide everything by 60. We get 28.7274. Tan alpha is VF1 over VW1. Now, when you do this, you're looking at substituting. So tan alpha is 20, then you still have VF1 over VW1. So I can multiply both sides by this one, which is VW, velocity of wheel 1. So here it will cancel. Even this side, I do the same. Times VW1. So these will cancel. So that I remain with VF1 is equal to this. VW1 tan 20. That's my first equation. Then I invite tan theta. Tan theta, looking at the velocity triangle that we have, is equal to VF1 over VW1 minus U1. So tan theta is equal to, what is my VF1? It's here in equation 1 as VW1 tan 20. So in place of V1, we put that. Below we have VW1 minus U1 is already here, 28.274. So let's cross multiply. I multiply both sides of the equal sign by this whole expression here. Meaning that on the left, I'll have tan 60, open brackets, VW1 minus 28.274 is equal to VW1 tan 20. Then you open the brackets, you have 1.732 VW1 minus 48.972 is equal to 0.364 VW1. So from here, we end up with V velocity of V1 as 35.798. Then VF1, from this, we said VF1 is equal to VW1 tan 20. So we substitute here and get this, because VW1 is 35.798. So 35.798 times tan 20, our answer for VF1 is 13.029. Now, to get the discharge, we're going to say area of flow times velocity of flow. So our area of flow here, if I want, I cannot write this. I can just write A1, which is representing everything there. Area of flow, A1 or pi D1 B1 times VF1. The whole of this is represented by 0.4 because it was already given in the question, so there's no need to struggle and stress about it. So multiply by VF1, velocity of flow 1, we already calculated it as 13.029. So then our discharge is 5.2116. It's in cubic meters per second. So there we have it. This is our value. Part B, the power. The power, the formula is density times discharge times VW1, U1. So power is equal to density is 1000. The discharge is the one we got there, 5.2116. Multiply by this VW1, 35.798, U1, the 28.274. So then we get our power as um, 5 5,274, 5,274,934.761 watts. If you express the same in kilowatts, it's 5,274,934. We're talking about 5,274.934 kilowatts. Part C, last one, we're looking at the hydraulic efficiency. Hydraulic efficiency is simply given by VW1 U1 over GH times 100. So VW1 is 35.798 times U1, which is 28.274. G is 9.81, so we plant it there. We're working against what height? It's 120 meters. So what we get here times 100. And hence we get our hydraulic efficiency as 85.98%. Once again, thank you very much for your patience. This is the end of our paper. This was fluid mechanics for July-August 2024 for both auto and HE heavy equipment, basically our mechanical program there.